Yeah, I finished the grading. So based on the grading, the problems, then let me explain the common problems in your homework assignment number 1. Yeah. First, the average is 65%, whole class average of this assignment. Yeah. And the biggest problem, most students didn't watch the hint videos. We have 2 hint videos. Yeah, yeah. Because when I did grading, those relatively hard questions I already explained in the hint videos. But most of the students, didn't use the correct way to solve. Yeah. So later today I will explain those questions, how to solve. Yeah. But at the same time, after I finish this class, I will post the complete solution. Yeah. Because after this class, you will have the midterm 2 assignments, part A, part B, 2 assignments available at 8 o'clock, yeah, right after this class. Yeah. And when you work on your midterm, the complete solutions of home assignment number 1 should be very useful. Yeah. So for all the questions, I provide the complete solutions. Yeah. So not just the one answer. You have many questions, you only need to provide short answers, right? But in my solution file, I write detailed solutions, yeah, how to solve it. Yeah. So I will post it in the midterm section. So in Canvas, I create a midterm exam module. Yeah. So under that module, you can find part A, the quiz, part B, computation questions, 15 computation questions. Then I will also put the solution file, the homework number 1 solution file in that module, okay, in that midterm module. So you can study, yeah. All right, so let's start. Yeah. Yeah, part A, concept questions. Yeah. All right. The first questions, many students missed this one. The answer is false. Yeah. Yeah. So here's the statement. Yeah. Look at this statement. We say that the repeated squaring method can never do worse than repeated cubing. Yeah. Here I can give you a simple counterexample. Yeah. Yeah. Because in class I remember regarding comparing these 2 methods, I remember I said somewhere, sometimes repeated squaring is better, sometimes repeated cubing is better. Yeah. And sometimes they are the same. So they, they perform the same. Yeah. These 3 cases. Yeah. Yeah. In general, so here, when the structure of this n number is close to power of 2, then the repeated squaring is better. better. Okay? Yeah. If it is close to power of 3, then repeated cubing is better. Okay? Yeah. Because you use the method that fits the structure well. Yeah. That's important. Here, I give you a simple example. Okay? All right. So let's look at a simple example. N equals 27. We know 27 is power of 3. Yeah. So here you can see repeated cubing should be better than repeated squaring. Yeah. All right. For repeated cubing, yeah, x to the 27th. Yeah. Let us use the cubing way to do the decomposition. First cube, second cube, third cube, and a fourth cube. Okay. Then, because each cube, 2 multiplications, 2 plus 2 plus 2, 6 multiplications. All right? Yeah. Let's look at the repeated squaring. All right. Repeat squaring, 27 equals 16 plus 8 plus 2 plus 1. Right? Yeah. So your x to the 27th, you need to write 68 x squared 1, but in order to get x to the 16th, you need 4 multiplications. All right. 4, after that you need 3 more. Okay, 3 dots here, so 4 plus 3, you get 7 multiplications. All right, yeah. So you can see this one is better. Repeated cubing is better. Yeah. The reason because the number is very close to, yeah, it is exactly the cubing structure. Yeah. When you have a cubing structure number, if you want to do the decomposition using the, squaring, binary representation, right? Yeah, the binary representation then, because the structure not fitting well, so you need to do more work, right? So if you choose the structure that fits perfectly, then you use fewer number of multiplications. That kind of understanding. Yeah. So that's the reason. Yeah. Yeah. All right. So this is the first question. Yeah. Second one. Yeah. Actually, this question. Yeah. Yeah. I saw several students miss this one, but this one we did in quiz 2. Yeah. So I didn't realize. So when I gave you in the homework assignment, yeah, because I couldn't remember all the questions. Yeah. But later I noticed this is question number 4 of quiz number 2. Similar, right? Yeah. Although the wording slightly different. Yeah. But here, I think the confusing part for those students who missed this one, after several hundred years. Yeah. But here we do not say, we say all the time. Yeah. Yeah. So then, relatively easier, but that one, so I put something, make distraction. Yeah. Make distraction. Yeah. 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 But, answer should be the same. No. Yeah. The reason is very simple. In our class, we prove it rigorously. We know the optimal solution n minus 1 comparisons. Yeah. Here, optimal means, no time limit, right? Yeah. It's an absolute optimal solution. Yeah. Yeah. Forever. It is correct forever. No matter hundreds of years, thousands of years, millions of years, always correct. Optimal solution. Yeah. That's the meaning. Yeah. All right. Otherwise, we cannot call it optimal. Otherwise, if we cannot prove it is absolutely the best solution, then we can only say, oh no, we don't know. We don't know. We don't know it's optimal or not. Yeah, that's possible. Many times we don't know if a given algorithm is optimal or not. Yeah, then we cannot call it optimal if we cannot prove it. Yeah. But this question is very simple, so we can prove it. Yeah. So that's why we can say, yeah, it is optimal. Yeah. All right, number 2. Yeah. Next question. This one, yes, this one, the correct answer is false. Yeah. But many students select true. So here, I need to explain the main point here. Yeah. In class, I explained, one place in the notes. Yeah. I remember at the end of the class, I explained there is a concept. All right. Because some students may wonder why sometimes the same statement, sometimes we treat it as a correct statement. Sometimes here we do not treat it completely correct. Yeah. All right. So here, let me emphasize that point again, because this point is very important. All right. The main difference is about, these two concepts. All right. One is a statement is correct or not. Another is a principle. We use it as a principle, okay? All right. Statement. If it is correct, we say a statement is correct. We mean it must be 100% correct. Okay? Yeah. So you cannot even find one counterexample. It's not allowed. Yeah. If you can find one counterexample, then we say it's incorrect. That's for the statement case. Okay? All right. But for the principle, so what's that principle? The principle, that is when we use in our real world life, we adopt this principle. Sometimes we adopt this principle, but sometimes we do not adopt this principle. Okay? Principle is something like a guideline. Okay? Sometimes we follow the guidelines, but sometimes we do not have to follow the guidelines, right? Sometimes because when we have some special situation, then we do not need to follow the usual guidelines. Yeah. So that's the principle. Principle, when we talk about that principle, not necessary. %100% correct. Okay? Yeah. That means we allow some exceptions. Okay? We allow. Exceptions. Yeah. All right. So in our problem solving, it's good enough, right? Yeah. Because the principle usually used in our, so usually it is used in our problem solving. In problem solving, if it is you know 90% correct, 90% correct, because we have a very good chance to do things right, right? Yeah. If you choose some special way, if you follow this direction, you know, to solve your problem, then you have 90% of the time correct. That's a good choice. Okay? So usually we are very satisfied, yeah, to use it as a guideline, right? Yeah, as a guideline. Yeah. So then it's okay. Okay? 90%. Yeah. So we can use it. All right. Yeah. So based on this understanding, now let's look at this. But here, when I write this sentence here, we treat it as a statement, right? Yeah. Because here, we do not say in principle or in general. If you do not see that kind of phrase, in general or usually, that kind of special word, yeah, in principle, that kind of thing, then we treat it as a statement. Okay? So here we use the statement way to understand. So to evaluate polynomial, the higher the degree it has, the more multiplications we need. Yeah. But actually we can find counterexample, right? Yeah. Because if we use the statement way to understand, it must be 100% correct. That means we do not allow any exception. We do not allow counterexample. Okay? All right. So here, let me consider counterexample. Okay? All right. Now, let me use x to the 8th. Yeah. Simple counterexample. Okay? Yeah. So here, look at the counterexample. All right. Counterexample, the higher one, the higher case, degree higher. Yeah. That is x to the 8th. X to the 8th, we know because we can do square 3 times, right? Yeah. 3 times, that means we need 3 multiplications. Then another one lower, x to the 7th. 7 lower than 8, right? Yeah. But to get x to the 7th, you need x to the 4th times x squared times x, right? Yeah. But x to the 4th, you need a 2 multiplication, right? Then you add 2 more. 2 plus 2, you need 4 multiplications. So you can see the lower the degree, the number of multiplications you used, actually you need to use more multiplications than the higher degree special case. So it's a counterexample. So if we use the statement way, we require 100% correctness. Then you cannot say this statement is correct, right? Yeah. But in our problem solving, if we use it as a principle, then no problem. Yeah. Yeah. Because for this sentence, most of the time it's correct. Okay? Yeah, we can say 90% of the time it is correct. Yeah. So we can use it as a guideline in our problem solving. Yeah. Yeah. That's okay. Yeah. So that's the main difference. Okay? So for those students who missed this question, yeah, because this kind of understanding is important. Yeah. Yeah. Otherwise you get confused. Why sometimes we can do it in this way? Yeah. Because in many of our examples, when we do size reduction, we take this principle. Yeah. When we do size reduction, we take this principle. Okay? Yeah. But it does not mean this statement is 100% correct. Yeah. So that's the understanding. Yeah. All right. Yeah. Next one. Yeah. So this one, the answer is B. Yeah. 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 Some students missed this one. Yeah. But because here I give you a specific number. I give you a specific number. If you use the result in our notes, so you may have some question. Yeah, if you use the results direct, because our result is log base 10 of n is in the little o of n to the d. Okay, so we only require d positive. Yeah, yeah. But if you use this result, still, it may not be right. Yeah. The question is, it may not be right. We don't know. Yeah, because when you use this little o, you consider n goes to infinity, right? Yeah. So this result is correct when n goes to infinity. Yeah. But here, n is a concrete number. So although it's an extremely large number, but still it is different from that infinity. Okay? So in that case, which one is larger? You don't know. Okay? So you need to calculate it. Yeah. If you do not calculate it, you may not know which one is larger. Yeah. Yeah. So in my grading, I didn't see. Most students didn't do the calculation. Yeah. So probably they just, use their own way to tell which one is larger. Yeah. Here, let me show you some simple calculation. Okay. All right. So for the first one, log base 10. Yeah. Let us write this n number in base 10 number. Yeah. Here, the original number is base 100 number, but 100 is 10 squared. All right. Then we use the algebraic property. Yeah. 10 to the 2 times 10 to the 10. Yeah. That algebraic property. Okay. Yeah. So here, we use this a to the m, then m equals a to the m times n. We use this property. Okay? All right. Yeah. So we treat this one integrated number integral number. Yeah. All right. So then you take log base 10. Base 10, yeah, because same base, right? Log base and exponential function base, same base. So something like cancellation. Yeah. So the base part is gone. So we only have the exponent part. Okay? Yeah. So that's the first number. The second one, yeah. All right. And we write this way, yeah, because we can compare in the same base to the comparison. Then we need to calculate 0.01. Yeah, this number is 1/millionth, right? So 1/1 million. Or we can write it 10 to the -6. That's 1/millionth. Okay, all right. Then we apply this algebraic property. Yeah. So we can write it as 10 to the times 10 to the -6. Okay, yeah. So then 10 to the 2 times 10 to the 4th. Okay, yeah. 10 to the 4th. Yeah. 10 to the 4th. Let me write one more step. 10, 20,000, right? 4 zeros after 2. 10 to the 20,000, the exponent number. But here, exponent number is 10, but here only 2. Okay, 2 less than 10, right? Yeah, less than 10 to the 11th, right? Yeah, because 2 less than 10. So you just 11. You compare here to 20,000. So you know the second one is much larger. Yeah. So based on this calculation, you can see B, yeah, is much larger. Okay. Yeah. The reason is because you cannot apply this our result directly. Yeah. Directly, it is dangerous sometimes, because that result is true for n infinity. The number you have here, it's not infinity. Not infinity, that means sometimes it is true, sometimes A is larger, sometimes B is larger. You don't know. You need to calculate it to see which one is larger. Yeah. Okay? All right. So that's this question. Yeah. All right. This question, yeah. This question, if you are familiar with Horner's rule, so this question, check your understanding on Horner's rule. Yeah. So you need to use the way we write it in the Horner's rule. Yeah. That structure, that special structure, the factorization special structure. Yeah. All right. So we write it. First factorization, x cubed a1. Yeah. But the second factorization, x to the 4th. So here you need to, do things slightly different from Horner's rule. Yeah. Another x to the 4th, right? Yeah. So actually, yeah, because we do another round factorization. Yeah, so that's here. Yeah. Then another round factorization. Yeah. Plus A5. See? Yeah. This way, yeah. So then when you calculate it, you need to do preparation, yeah, because you use x cubed x to the fourth, yeah, many times. So in your preparation step, you need to calculate x cubed x to the fourth. All right. X cubed, you need two multiplications, right? Yeah. Because x cubed, you need 1 to get x squared. After you get x squared, you need another 1 to get x cubed. So you need 2. But because you already have x squared, you just need 1 more to get x to the fourth. Okay? So total, this preparation step, you need 3 multiplications. All right. Then you count. Yeah. Because after you get the x cubed, then you can use these two numbers directly. Yeah. So then you count 1 here, 1, 1, and 1. Okay, 5. Yeah. So your total number of multiplication, 3 plus 5, 8. 8 multiplications. Okay, 8 multiplications. So the correct answer is 8. Yeah, but several students, some students give me 7, some students give me 9 or more. Okay, so in these two cases, if you give 7 I give you a partial credit. Yeah, 2 points. Okay, yeah, here also 2 points. Yeah, but A, no point. Yeah, so because 7 or 9, so probably you're counting, slightly wrong. Okay, so when you count your final number, you missed a little bit. Yeah, so for that reason, I give you a partial credit. 2 points. Yeah. Yeah. All right. Yeah. So that's the concept part. Yeah. All right. Then a quiz question. Yeah. So this I select from the quiz 1. So I because this one relatively hard, so I explain a little bit. Yeah. For most other questions, pretty easy. Yeah. Yeah. After you see the answers, I think you can understand easily for most other questions. Yeah. But this one, I want to explain why. Yeah. 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 So here, is it possible, always possible, yeah, for any positive integer one can find special any, yeah, I mean, here the wording is, yeah, just a minute, yeah, any part, yeah. Yeah, so that's not what I want to, yeah, not any part, yeah, that's something, right, because to make this true, n should be very large. If n is small, then we cannot do it, right? So any part, in that way, probably your answer, yeah, I need to double check, yeah. Yeah. So this question probably, my answer, yeah, because I should say, yeah, not any, yeah, so any positive integer, then it may not be true. Yeah. The question is, there exists some positive integer n, not any. Okay, there exists some positive integer n. Yeah, then you can do it. Not any. Yeah. Because that n number should be sufficiently large. So here, actually, not some. So actually we should say, because when n sufficiently large, so we learned that concept. What's the meaning of sufficiently large? When n sufficiently large, then it is correct. If it's not sufficiently large, that means you can find, you can find some n0, okay, positive integer n0, such that when n greater equal to n0, it is correct. So this statement, if we say when n sufficiently large, it is correct, then it's yes. If n is not sufficiently large, then it may not be correct. May not be correct. Yeah. All right. Yeah. I will go back to check answers because I can see your answers. Yeah. If I see you answer no, I will give you 4 points back. Okay? So I will modify. Yeah. I will check one by one. Okay? I will check your answers one by one. If you choose no on this question, I will give you 4 points back. But if you choose yes, so I do not change anything. Okay? So I do not change anything. If you say no, so I just add 4 points to your grade. Yeah, because I didn't realize I should use this phrase. Yeah, not any positive. Yeah, that's the main difference. Yeah. All right. So so I find no problem. Yeah. All right. That's part A. Next, we need to do part B. Yeah, part B is the the hard part. Yeah. We have some basic questions and we have some challenging questions. Yeah. Let me look at the time. Yeah. Before the break time, I have about 30 minutes before the break time. Yeah. Yeah. So let me explain a few questions before the break time. Yeah. Computation questions. Right. The first one is this one. This question, number 17. Yeah. So don't worry. For some of the questions, I do not explain today because I will post the full solution, the solution file covering all the questions. Yeah. But for the questions, I saw a lot of common errors. So then I explain here. Okay. Yeah. So the common error for this one is regarding this condition. Regarding this condition. Yeah. Yeah. Many students, many of you did not use this condition. Okay? Yeah. You need to use this condition. Yeah. Need to use this condition. And many of you ignore this condition. Yeah. Although in our problem solving, we can ignore this condition temporarily, but after that you need to add this condition back. But I saw, most of you forgot to add this condition back. Yeah. All right. So without this condition, we have formula, right? Yeah, so we apply, yeah, yeah. Maximum, minimum, find them at the same time, yeah. But some students apply the formula not quite right. The correct version is ceiling function -2, yeah. And some students give me the wrong version. They use the brackets. Bracket actually means the floor function. If you use the bracket, yeah, actually you use the floor function. So a couple students use the, without that -2. Yeah, a couple students use this version. Or, yeah. So they use this version. Yeah, several students. Yeah. So the correct version is this one. Okay, this one. So because you need to use n equals 17. Yeah. 3 times 17 -2. Yeah. 51 over 2, 52. So that's 26 minus 2 equals 24. Yeah. So those students use this formula, they give me 25. Yeah. Many students give me answer 25. Okay? Yeah. But that's the without that condition. Then you need to, after that, you need to add that condition back with that condition. Okay? With that condition. All right. When you look at these 5 inequalities, actually, this condition gives you the results of 5 comparisons, 5 useful comparisons, right? Yeah, if you look at them, so, all of them are useful. Okay? Yeah. All of them are useful. That means that condition you can save. You can save 5 comparisons from it. Okay? So your answer should be 24 minus 5 equals 19. Yeah. Correct it. Make corrections. Only a small number of students gave me this 19 answer. Small number of students. Most students gave me this 25. Yeah. A few students gave me 24. Yeah. But you need to correct it. You need to make correction by the given condition. Yeah. So that is the common error for this question. Okay? Yeah. All right. This one, yeah, the answer is 8, the best answer here. The best answer, 8 multiplications. But most students give me 9 multiplications. That means, not the best. Not the best. Okay? So because you can do one better than that. Yeah. Yeah. But a few students give me more than 9. Yeah. More than 9, then, you are far away from the correct answers. Yeah. So here, let me explain. So why so many students give me this 9? Yeah. All right. The reason is, some students, if you apply the repeated squaring directly, you get that 9. directly, you get this 9 solution. Yeah, no problem, no problem. Okay, yeah. And one student referred to one method we used in the textbook. Yeah, one student, yeah, referred, because in our chapter 6, yeah, 6.4, section 6.4, yeah, there is a topic called binary exponentiation. Yeah, okay, but actually this algorithm in exactly the same as our repeated squaring. Okay, yeah, or we can call it generalization. Okay, actually it is a generalization of the repeated squaring. But the generalization, we, in our notes, we use the same name. Yeah. Although I didn't use the binary exponentiation, yeah, but I use the same name. Yeah. We still use the repeated squaring. So we extend it, remember? Yeah. Because repeated squaring is supposed to be used for n equals power of 2, then repeated squaring. But later we extend it for any positive integer n. We extend it, so we still call it repeated squaring. Yeah. But actually that version in the textbook, it has a different name called a binary exponentiation. Yeah. All right. Then, so one student, giving me the, refer to this binary exponentiation, then use the formula log base 2 of n, yeah, because this is not an integer. Yeah. So then, take ceiling function to give the answer. Yeah. So, 1 or 2 students use this expression to give me, the final answer related to this binary exponentiation. Actually, this is not the correct formula. Okay? Slightly different, not exact, very close. So this formula, very close, but not exact. But not exact. Yeah. The exact version is this. Exact version, actually we learn it. Yeah. In one of our computing problems, we learn it. So in that problem, I gave you the exact version. Yeah. So that one is, we call in our binary bits problem. In our binary bits problem, the version is 1 plus floor function, but you need to add a 1. Okay? So this version is different from that version. This is exact version. Okay? Yeah. If you use this number to calculate the number of multiplications in your binary exponential, then your answer is correct. Then you will get a 9, okay? Then you will get that 9. Yeah. All right. Yeah. Oh, actually not. You will get 8. Yeah. 7. Sorry, 6. Yeah. Actually, yeah. Not right. Because 108 greater than 6. 6 point something. So 6. 1 plus 6, 7. Oh, yeah, 7. But the answer is Answer is 8. Yeah, still not that 9. Yeah, yeah, yeah. All right, but we have a answer 8 version. Yeah. Okay, answer 8 version. Answer 8 version. Yeah, actually, one way we can use repeated cubing, so we can get answer 8 version. Yeah, yeah. So let me show you. Yeah, yeah. 36 times 36. 36. Okay. Yeah. $12. All right. Yeah. And yeah. Yeah. So then, 7. Yeah. Sorry. This way we need a 7. Yeah. All right. Because x to the 4th we need a 2, right? Yeah. Oh yeah, 2. Okay. Yeah. Not 7. 8. Yeah. Because we need a 2 for x to the 4th. Yeah. Then each one we need a 2. 2, 2, 2, and a 2, 4 times. So then 8. Yeah. Right? Yeah. 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 But some students put a 7. So then I ask them, how do you get 7? Okay, can you get a 7? Yeah. Yeah. I saw a few students give me the answer 7, although I give them partial credit. Yeah. But if those students can really show me some way to use 7 multiplications to calculate this monomial, then I can give them full credit. Okay? Yeah. So you need to really convince me you can use 7 multiplications to find this monomial. Then I will be very happy to give you full credit. Okay? Yeah. Yeah. So I remember, at least 3 students used the 7 as the answer. Yeah. Yeah. So you need to think about if you can really make it or not. So if you can make it, then you let me know. So I will give you full credit. Yeah. Yeah. Probably not just the full credit. I would like to give you, after the full credit, I would like to give you 2 bonus points. Okay? Yeah, if you can do it in 7 multiplications. Yeah. Yeah. All right? Yeah. So that's this question. Yeah. Yeah. Then the binary exponentiation. Yeah, then I will check this because the answer here still slightly different. Yeah. Slightly different related to the binary exponentiation. I will double check. Yeah. Yeah. Some relationship, but the problem is not exact. So I need to double check. Yeah. The answer, yeah, why the specific way and the formula way is different. Yeah. So after I find the problem, so I, if I can find time, I will talk to you. Yeah. So here, some gap. Yeah. So here, let me write here. Yeah. Some gap. Gap we need to fix. Yeah. Okay. All right. Yeah. This question. This question. Also, some students very close. very close. Yeah. And the answer is 10 multiplications. Yeah. Many students give me 11 multiplications. Very close. Yeah. Yeah. Even 10 multiplications, we have different ways. Yeah. Yeah. All right. So here, the simple way. Okay. Yeah. Here, let's consider simple way. Yeah. All right. X 37, right? Yeah. Plus A times 77, but 77 we want to split. Split it. Oh. 37 we want to reuse this thread because after we spend a lot of resource to calculate the first term, x37, then we don't want to, repeat the same amount of work. We want to reuse that number. All right. So based on the reuse way, 40. Okay? We split in this way. Okay? Split in this way. So that tells us we need to calculate these two expressions. One is x to the 37th. Another is x to the 40th. Okay? Yeah. All right. Then we prepare. All right. Because when we do the squaring operation, the preparation, in this preparation, we need 5 multiplications. Okay, all right. Yeah. The first step. Then we are ready to calculate x to the 37th. Yeah. X to the 32nd, right, times x to the 4th. Okay. Yeah. Then x, right? Yeah. Actually, this is x to the 36, right? Yeah. This is x to the 36. Yeah. Or yeah. So yeah, you can do different. All right. So here, x to the 40. We can use x to the 32nd, x to the 8th. Okay, all right. Now you can see you need 2 multiplication here, but 1 more multiplication here, right? Yeah. Then for this final representation, you need 2 more, right? Yeah. Here, 2 more. Yeah. So the total 5 plus 2 plus 2 plus 1. So you get 10 multiplications. Yeah. 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 Now, many students show me step by step, slightly different from this one. Yeah. Slightly different from this one, but they used one more than the best answer. Yeah. So because we want to get the best answer, right? Yeah. So if you can get the best answer, you get a full credit. So if it's not best answer, you can only get a partial credit. Okay? Yeah. All right. That's this question. Yeah, let me see the time. Okay. Yeah. So let me see if I can do one more question before the break time. Yeah. So let's do this one before the break time. Yeah. All right. This one. Common problem. Yeah. Common problem. All right. Yeah. Still, the common error occurs in this condition. Yeah. All right. So although in our first version we can ignore, okay, but when you ignore it, it's a temporary ignore, right? It's not a permanent ignore. Yeah. Because we should do the temporary ignore. But most students, they did permanent ignoring, permanent. Yeah. So they never add that condition back. That's the common error. Yeah. So so many students, more than half of you. Yeah. So close to 70%, 80%. Yeah, close to 80%. Yeah, because so here still without that condition. Okay. Yeah, first we consider without that condition. So use this formula. Okay. Yeah, that's the maximum number of inversions. Maximum number of inversions. This one. 23, 22. Okay. Yeah. 253. Okay. And most students just give me 253. Okay. Yeah. All right. But you need to know the corresponding input data for this situation, the maximum number inversion situation. That's the descending order. Your input in descending order, then you have that solution, right? So let's look at the descending order. Descending order, okay? Yeah? Yeah. If we use, all right, so here, if we use the position 1, 2, 3, ... Okay, all right. 11, 12, 13, ... Okay. 22, 23. Okay, all right, this and the other. All right. Then, all right. X, 12. Yeah. Yeah. This element is in the middle, right? Yeah. Right in the middle. Yeah. That means its left-hand side there are 11 elements. Its right-hand side also 11 elements, right? So this position is in the middle. All right. All right. Then, when the array is in descending order, yeah, that means this X12 is in place, right? Because this position, if you make ascending order, the same position, right? X12 is in the same position. That means it's in place. It's a final, yeah. If you sort it, this is the sorted case. After you sort it, X12 stays at the same place, right? Yeah. Same place. Then it violates this requirement, okay? Because our requirement is X12 is not in place. That means this descending order input you should change. You should change it. Should change it to make X12 not in place. Not in place. Okay? All right. But how to change? Yeah. Now, you just make one small change. Do not do big change. do some small change that does not impact many other elements. All right, so one change you can do, swap X12 with one of its adjacent. Here you can swap X12 and X13. So swap X12 and X13. If you swap with X11, it's also okay. So, or another option you can do, swap X12 and X11, just one of its adjacent elements. Because when you do that swap, okay, you make X12 out of place, right? Yeah, not in place anymore, out of place. Yeah, okay, so, X13 here, X12 here, yeah, out of place. Yeah. But the only change is local change, yeah, because you swap two adjacent elements. Your change is local change. Local change only change this inversion. Okay, this inversion. Before swap, you have an inversion, right? X12, X13 inversion. This inversion is gone. After swap. After the swap. Okay? Yeah? Yeah, because after swap, if you look at this pair, they are in order, right? The smaller element is before the larger element. So it's not inversion. The inversion is gone. Okay? All right. That means your swap, you reduce inversion by 1. Yeah. Yeah. Before the swap, you have 253 inversion. After swap, you minus 1. You have 252 inversion. Okay? Yeah, you have 2 inversions. One reduction. 1 inversion reduction. So your answer is 252. Yeah. So that is the right way to solve this problem. Okay, you need one more. Yeah, but you need to understand what you are doing. I think why those students. Yeah, in my hints, in my hint video, I give you this idea. But I feel why those students didn't use this idea, because they couldn't understand the second half. The swapping. What's the meaning? What are you doing here? Yeah, because they didn't understand. So they skip it. Yeah. So here, this is the with case. Yeah. Yeah. With case. Yeah. So that's the reason, those 70 to 80% students, they stop after they got a 253. Then they stop. Okay. All right. Yeah. Let me give you a break. Yeah. So because I use a little more time, so let us restart our second half at 7:05. Yeah, let me give you 5 more.